Okay, cool. So yeah, welcome everybody. This is the last lecture because tomorrow we have the open problem session, which we also won't record. And on Friday, we'll see if we have a session or not, depending on how many open problems we get. Okay, so in this last lecture, I really just want to present one result, which is a recent work of Conlon, Ferber, and then a later development by Yuval Vigderson, who's in the audience, I think. So if you have any questions, you can also just ask him. So let's begin with this development. And it's really just about the multicolor diagonal Ramsey numbers. And in case you have forgotten what Ramsey numbers were, let me just remind you again. So we are interested in this number R of t semicolon L, which is the minimum number of vertices, minimum n, for which in every edge coloring of the complete graph on n vertices using L colors, there exists a monochromatic KT. Actually I can just simplify it. So there exists, this is much simpler right now because we only have one parameter t. So there exists a monochromatic clique of size t. So for example, here we have 6 vertices, so we have K6, and we have colored the edges using 3 colors. And you see that there exists a monochromatic triangle, but this is just a very special coloring. If you, for example, just change this one edge to green, then you don't have any monochromatic triangles. So this implies that R of 3, L is strictly bigger than 5, right? Because we want to make sure that for all colorings, there exists some monochromatic triangle. Well, here L should be 3. In fact, we know exactly what this number is. I mentioned this in the third lecture, I believe, that this number is known to be exactly equal to 17. So if you three color 17, three color the complete graph on 17 vertices, then you will always have a monochromatic triangle. But if there is a coloring of a 16 vertex complete graph where you don't have any monochromatic triangles. And this is in fact the only known multicolor diagonal Ramsey number, which is known exactly for L greater than 2. For 2 color, we saw some small examples as well. And really, this is the main thing we will focus on, more than 2 colors. So this whole lecture is about multicolor diagonal Ramsey numbers where the number of colors is strictly bigger than 2. And we also saw some general upper bounds and lower bounds on Ramsey numbers. So for example, the classical Erdős-Ekerés bound implies this exponential upper bound with base L to the L on the number. And a random L coloring of the complete graph on these many vertices can be shown to have no monochromatic KTs with probability greater than 0. So this gives you the lower bound, right? So this is the basic stuff we saw in the third lecture. Now, sadly, the upper bound has not been improved at all so far. As in, you can maybe improve for the 2 color, you can improve it by a bit, but essentially it's still the exponential function with base L to the L. But very recently, there have been some exciting development in the lower bound. So the lower bound has been improved just a few months back, and this whole lecture is about that improvement. So what exactly is the new lower bound and how do we prove it? And what role finite geometry plays in that improvement. Okay, so first let me tell you that for L greater than 2, you can actually improve this lower bound by a very simple argument. And this was observed by Lefman in 1987, who showed that you can sort of get an inductive lower bound on this Ramsey number. So if you have L1 plus L2 colors, then you can show that this Ramsey number is strictly bigger than the Ramsey number with L1 colors multiplied by the Ramsey number with L2 colors. And this is just a nice exercise, especially for those who have not seen Ramsey numbers before, so you're still getting comfortable with what these things are. Try to prove this just from the definition. Okay, and from this inductive thing, you can actually prove slightly better lower bounds. So for example, if your number of colors is a multiple of 3 times k, then you can just repeatedly use the bound for r of t comma 3. You can add 3k times, and so that shows up here, right? Similarly, if you have 3k plus 1 colors, then you can write this as, this thing is 3 times k minus 1 plus 4. So you can take the Ramsey number with 3 colors k minus 1 times and the Ramsey number with 2 colors twice to get this bound. Right. So, and it turns out if you think about this and you just do some computation, these are the best possible lower bounds you can obtain using this result and the previous one. Okay, so since then, since 1987, I guess many people thought about this problem, but there was really no improvement. So this is where we stood until a few months back, and that's when the new result was proved by David Conlon and Asa Ferber. And later on, Yuval Wigderson observed something interesting and gave an argument that improved their bound even further. And so currently the best bound we have, the best lower bound we have is the following. So here we have the Ramsey number t comma L, at least this thing raised to the power t minus little o of t. So essentially just t, right? So this is the base of the exponent. And maybe it's not so easy to see that this is actually an improvement. So yeah, let's just check. For L equal to 3, the new bound gives us 2 to the 9 over 8, 7 over 8 to the t minus little o of t. And the previous one was square root 3 to the power t. And you can convince yourself or just check somewhere that this number is actually bigger than square root of 3. And then you can check for a larger number of colors also that really this is an improvement. So it's an exponential improvement. It's an improvement in the base of the exponent in the lower bound of this Ramsey number. Cool. And the main idea behind this proof is in fact the thing that we already saw when we were talking about off-diagonal Ramsey numbers, where we said that if you have a clique-free graph which might have a really large independence number, but it has very few independent sets of a certain size. Here, for example, I can be more precise. Few independent sets of size at most t. So if you have such a graph, so somehow you can construct such a graph, then there is a trick or there's an argument by Yuval that tells you that you can really improve the lower bounds on these multicolor diagonal Ramsey numbers. And this is the precise statement. Okay, so that's the main idea, but let's just go through what the precise new result is. So here's a lemma. This is from Wigderson 2020, let's say, which says the following. Okay, so say you have a graph, which is, you say you have a graph which is kt free, so it does not have any complete graphs on t vertices at subgraphs. On exponentially many vertices, I'm going to write 2 to the t plus little o of t vertices. So everywhere we will assume t goes to infinity. Those are the asymptotics we are talking about. And this might look very artificial to you that I'm already picking like a graph on some special sort of number of vertices. But yeah, it's just for convenience. I'm going to write it like this. You can write down this whole thing in a much more general form where this thing is just some number n, but it's okay. I'm going to ignore that. So we have a graph on, let's say, roughly 2 to the t vertices, such that the number of independent sets it has, so the number of sets of size at most t, which have no edges between them. So the number of independent sets of size at most t is 2 to the at squared, where I should write down that a is some constant between 0 and 1. So this is the number of vertices, and trivially, if you just pick t elements from a set of these many elements, then you will get size 2 to the t squared, right? So trivially, you'll have 2 to the t squared many t element subsets, where it says that you have very few independent sets. And this thing is measured by this constant a, which is strictly less than 1. So that's the point. So say you have such a graph, then there will be an argument, which I will talk about in the second half of this lecture, which says you can prove the following lower bound on this Ramsey number. Okay, so any graph, give me any graph with these properties, and I can give you a lower bound on this Ramsey number. Okay, and the second part, or well, in fact, I'll actually look at lemma 2 first. So then what we are left with is actually constructing such a graph, and constructing such a graph with the smallest possible a. Because if a is really small, then yeah, that's when this bound is big, right? You want a to be as small as possible. It turns out the best known construction, which is in fact due to Conlon and Ferber, is with a equal to 5 over 8. And this is the construction we will talk about, because this comes from finite geometry. And in fact, it will come from some finite geometries that we have already seen in this course. And then later on, I will tell you that this general argument, lemma 1, which has nothing to do with finite geometry, it's a very, very general argument. Okay, so that's the aim of this lecture, to prove these two lemmas. And finally, if you just plug in a equal to 5 over 8 in this, then you get the result of Conlon and Ferber. You can check that calculation yourself. Okay, so that's what we are going to do. Any questions so far? What's the plan and what exactly is the result?
Hello. I was wondering if this A 5/8 is tight.
Is tight? What do you mean?
Yeah. Or like if the A could be made smaller.
Oh yeah, that's the open problem, right? If you can make a
Okay.
smaller, you improve their results.
Okay.
So this is the best A we know so far, and that's the construction of Conlon and Ferber that we'll talk about. But if you can improve this A to something smaller, then that's amazing. That just improves this result. Right, so we have sort of dissected this whole result into these two independent bits. And now all you have to do is use this as a lemma 1 as a black box and just construct new graphs, new KT free graphs on 2 to the t plus little of t vertices, which have some, these many independent sets, and a is strictly less than 5 over 8. In fact, if you can do it for a equal to half, I believe that will then match the Ramsey number for the two colors also, right? You divide n by m, but anyway, I guess let's ignore that. Anyway, so this is the big open problem. Okay, so open problem, construction with a strictly less than 5 over 8. And I don't believe this will be tight, as in I don't think you can just prove I don't think you can just prove that this 5 or 8 would be tight. Yeah, that will be strange. Okay, any other questions? No? Cool. So we start with lemma 2. So we actually start with the construction of this nice graph. And you'll see how similar it is to the sort of stuff we have seen in the previous lectures. So essentially, it will use polar spaces. So this will use polar spaces, even though, again, you don't see polar spaces being mentioned in any of the papers. You don't really have to mention them, but yeah, it will be good to understand what exactly these graphs are. Okay, and here is the construction. So let's get through this together. We assume that this t is even, which matters for our construction, but for the lower bound, ultimately it won't matter, right? If you prove this lower bound for just all the even t, then for the odd t's, you also get the same asymptotic lower bound. So it doesn't really matter. And now I pick a bilinear form. So I pick a bilinear form which looks like this. And the main thing to note is that this is an alternating bilinear form, and we are picking the field F2. So it's an alternating bilinear form in this vector space. In particular, let's just note this thing again, that beta of u comma u is 0 for all u. So it's an alternating bilinear form. If you just plug in x equal to y here, you get 0. And the second thing to note is that this is a non-degenerate alternating bilinear form, which means that this map u goes to u perp, which is just defined again as all those vectors for which beta of u comma v is 0 for all u in u. So this thing is a polarity. In fact, if you remember the lecture on polar spaces, then what we really have here is the symplectic polar space. But it's okay if you don't remember. Just very concretely, we have this bilinear form, this function. And now our vertex set is just all the vectors. So the full vector space, though I guess for convenience, let me ignore the 0 vector. So in fact, this is just isomorphic to the projective space of one lower dimension, because we are working over F2, right? So in the binary field, there's only one non-zero scalar multiple of any vector. So it's the same thing. So we have a graph on the points of this t minus 3-dimensional projective space, where we define adjacency by non-orthogonality. So x comma y are adjacent if they are not orthogonal to each other, if beta of x comma y is equal to 1. That's the graph. So earlier we were mostly looking at the orthogonality graph, right, where beta of x comma y is 0. Let's look at the non-orthogonality graph for now. And my claim is that this graph, this really simple looking graph, has the required property. So it has no cliques of size t, and it has very few independent sets of size at most t. That's the claim. Any questions on the construction? If you have seen the paper of Conlon and Ferber, you might not recognize this graph. I have really sort of rephrased the construction, and maybe I'll mention the original construction at some point, but let's work with this one. It's actually equivalent to what they have done in their paper. Okay, if not, then let's just prove the properties that we want. So the first thing we want is that this graph has no cliques of size t, right? Okay, so let's assume there is a clique, say v1 up to vm form a clique where m is less than equal to t, or well, in fact, forget m is less than equal to t. So say we have a clique where m is even. Now, what we will show, so we claim that this implies that this set is linearly independent. So if we have a clique of size, an even size clique in our graph, then I claim that this clique corresponds to a set of linearly independent vectors inside my vector space. So my vector space was a t minus 2-dimensional vector space over F2. So this implies that M has to be at most t minus 2, right? So this implies that there won't be any cliques of size t, if I can prove this claim. Okay. Cool. So let's prove that. Say they are not linearly independent. So which just means that you have some linear combination which is 0. So say I equal to 1 to m. Something went wrong. So say this is 0 for some coefficients alphas. I want to prove that all of these alphas are 0. And now we just do the standard thing that we did earlier. Just take the dot product with each vi on both sides. So just apply the transformation, the bilinear form beta. So beta of this sum with vj is equal to 0, but it's also equal to the sum of all alpha I equal to 1 to m minus alpha j, right? Because note we have a clique, which implies that beta of vi vj, so beta of vi vj is 1, right? So in our graph, this was the adjacency. So all of them are non-orthogonal to each other, but also this is when I is not equal to j. And beta of vi comma vi is equal to 0. Right, so I'm just using that. So this implies, so now we have that this thing is 0 for all j. Now what do? Just sum up all of these equations, right? We have these different j's from 1 up to m. Just sum all these equations up, and then you get the following. M minus 1 multiplied by sum of alpha I is equal to 0. And now comes the observation that we chose m such that m was even. So this thing is odd, right? And we are working over the binary field. We are working over F2. So this thing is non-zero. So this is not equal to 0, which implies that this thing should be 0. And now you just plug in this equal to 0 back in these equations. So this thing is 0 in all of these equations, which implies alpha j is 0 for all j. Right? Very simple proof. And basically the same thing that we did before. Cool. So this was easy. We have a graph. I should note that the number of vertices in the graph is exponential, which what we wanted, right? 2 minus 2, in fact, or well, minus 1, whatever. So we have a graph on exponentially many vertices, which is in terms of t, and which is kt free. Now we want to count the number of independent sets in this graph. And later on, we will use that. So this is my second claim. So my lemma is that the number of independent sets in this graph of size at most t is at most this number. So here, this 5 over 8 is the A that we were talking about. Okay, So how do we prove that? What do the independent sets look like? So say we have an independent set. So say V1 up to Vm is an independent set. Here I mean independent in the graph, right? Not linearly independent. So say we have an independent set in the graph and m is less than equal to t. Then what do we have? Well, this time beta of vi vj is 0 for all I comma j. Right? This is an independent set where we have non-edges now. So what we have is a bunch of pairwise orthogonal vectors. Or if you remember the polar space stuff from before, what we have is a non-isotropic, is a totally isotropic subspace, right? But it doesn't matter if you don't remember that. Now, the way I'm going to count the independent sets is by observing that this thing spans a subspace. So this V1, Vm is a subspace of, say, dimension R. So let's call this R the rank. Okay, so here's our approach for actually counting the independent sets. I'm going to count all the independent sets of size m, or I'm going to estimate all the independent sets of size m that have rank R. And once I have done that for some given R, then I can just sum over all possible values of the rank, and then that gives you an estimate, right? So all possible values of R. For each R, I'm going to give you an estimate on the number of such independent sets. That's the plan. Okay, so let's do that. Let's count the number of independent sets of the rank R. Cool, that's the plan. So this is a question mark. Okay. How do we do that? Well, since the span, so since the subspace spanned by these vectors has dimension R, has rank R, there must exist some R elements here which are linearly independent, right? There must be a basis. And without loss of generality, let's just assume, so without loss of generality, let's assume that V1 up to V R are linearly independent. And then the remaining ones, so this implies that the remaining elements, so V of R plus 1 up to V of V sub m minus R, they all lie in this span, in this R dimensional subspace, right? So we are first going to estimate the number of ways of picking these R linearly independent vectors, and then we are going to pick these vectors one by one. Okay, so say somehow we have picked these vectors, then can you tell me in the chat, anyone, how many choices are there for these vectors? So once we have picked the first R, and that we'll estimate separately, then can you tell me what's the number here? So what's the number of choices for picking these elements? Just anyone, if you want to do that calculation. So this thing has size 2 to the R. Anyone? You can also unmute yourself if you want. We just want an estimate. We don't need an exact calculation, but of course that's fine. So you want Yes. Yeah, exactly. That's the question. So we want to pick these. Once, say we have picked the first R, we're going to look at that later. Say we have picked these elements, then once we have done that, how many choices are there for these elements? Where I claim that they all belong to an R-dimensional subspace. For the last one, should the VM, sorry, my bad. Yeah, thanks, Sam. Yeah. 2 to the R, choose M minus R. Yeah, sure. You just pick any vectors, right? You just pick any M minus R vectors there. And that can be estimated by just 2 to the R to the power of M minus R also, right? You can even have repetition. I just want some estimate. So we are going to estimate this final thing by 2 to the R raised to the power M minus R. Okay, but 2 to the R choose M minus R is in fact correct because you can pick any M minus R element subset. So now the main thing is how many such vectors can be picked. And that's where you really use some geometry, right? So let me try to draw a diagram. So say we have picked V1, then we have this thing, this hyperplane, which is V perp, V1 perp, right? So once we have picked V1, your V2 should belong to V1 perp, right? Because V1 and V2 are orthogonal. So all of these are pairwise orthogonal to each other. So once you have picked V1, then V2 belongs to V1 perp. And once you have picked V1 and V2, then, so say this is V2 perp, then V3 should belong to V1, V2 perp, intersection V1 perp. So V2 perp intersection V1 perp. So once you have picked V1, so the number of choices for V1 is 2 to the t minus 2. And then once you have picked V1, the number of choices of V2 is just 2 to the t minus 2 minus 1, because now we have a hyperplane. And then once you have picked these two, then the number of choices for the third vector is just this minus 2. And these are all linearly independent. We assume that these are all linearly independent. So at every step, when you take the perp, you're reducing the dimension of your space of choices by 1. So the cardinality of V1 perp intersection V2 perp, or in fact, let me just say dimension. So on intersection Vi perp is simply t minus 2 minus I, because these are linearly independent. So basically you have these linearly independent hyperplanes. Okay, so finally, what's the number? So this is the number of choices, 2 to the t. Yeah, you can just sum all of these things up directly. You have t minus 2 minus r times r minus 1 over 2. And the previous number, which was 2 to the r times m minus r. So in the end, you have 2 to the power of, oh, sorry, this t minus 2 should be multiplied by r. So you have t times r plus m times r, and then minus 3r square over 2. You have plus r over 2. Yeah. So you have minus 2r, so minus 3 over 2r. Someone has a question, I guess, if you unmuted yourself.
I believe maybe the dimension should be 1 higher, I think. If you just check for I equals 2, for example.
For I equals...
Or... No. No, I was mistaken. Yeah, sorry.
Right, so if V1, yeah, I'm looking at the dimension of the perp. right? I'm not looking at the, yeah. So maybe the confusion is that here we
Yeah.
have these many choices, and yeah, from this step we see v1 perp. For that we have, yeah. So for the ith vector, for the I plus 1th vector, we have these many choices, 2 to the these many choices. Yeah. Is that okay, Sam?
Yeah, I agree.
Okay,
I'm sorry.
good. Yeah. So this is the number. So this is the number of choices we have for independent sets of rank R, right? It's like it's an estimate. It's an upper bound. Okay, and now we can just sum up over all values of R as well. But firstly, let me just use the fact that M was less than equal to T to write this down as 2 to the 2TR minus 3R squared over 2 plus 3R over 2. And in fact, that is less than equal to something, and you can tell me what this is. So the exponent here is a quadratic function in R of the form, which looks like this. So we have the form, it's a quadratic function that goes like this. This is 0, and this is something else, whatever, some root alpha. Because we have a quadratic function of the form this thing. So this function actually increases up to this value. So we could have just estimated this by that maximum value, right? We can do that. And that maximum value turns out to be R equal to, I believe, something like 40 minus, let me just write it down. It's roughly 2t over 3, I believe. Over 3 minus half, something like this. So we could just plug in R equal to 2t over 3 minus half, and that's a nice, hopefully a nice estimate. But now that we have gone through this whole course of finite geometry, can you tell me if this is good, or can we actually do something better? Can we pick some other value of R where this function is actually maximized? So anything in the chat? Of course, not from Yuval because it's from his paper, so he should know what this is. But anyone else? So I'm saying the function actually never reaches this point. The function is, in fact, maximized at some other point because of some geometry reasoning that we saw earlier. So this R is the rank of the independent set. What's the maximum possible value of R? I'm saying it's not 2/3 of the dimension. It's actually something smaller. Why do you think about that? Exactly. So let me add another page. Exactly. So as Sahu has said in the chat, R is in fact at most t minus 2 over 2. Right? This is the maximum dimension of a totally isotropic subspace. We have a polarity. We have this U contained in U perp. So the dimension is at most half of the vector space dimension. So this function is maximized at R equal to t minus 2 over 2. Okay, so finally, because we have not only 3 minutes, yeah, okay, I can do that estimate now. Let's plug in R equal to t minus 2 over 2 there. And then I believe you should get something like 2 to the yeah, I think you should get something like 2 to the 5 over 8, what we wanted, plus little o of t squared of rank R, right? So yeah, R is t over 2. you get t squared over 2 minus 3t squared. T squared minus 3. No, you don't get this. Yeah, I'm lying here, I guess. Interesting. So if you plug in, no, you do get this. So 3t squared over 4. Whew.
I'm sorry, what's wrong?
Yeah, is it correct? Maybe in my head I'm trying to do it and then I'm making a mistake here. So if you plug in r equals t over 2. Yeah, it's correct. Okay, sorry. Yeah, so this thing, yeah, in my head I was doing it wrong. Yeah, so this thing becomes 3 over 8 and this thing becomes 1. So you get 5 over 8. Yeah, it's correct. Okay, so all good. Okay, so you get this estimate then on the number of independent sets of rank R. But now R can have many possibilities. And in fact, this is an estimate on the number of independent sets of size M. And M can also have many possibilities, but those things hardly matter because you can multiply by all possible values of M. So you're summing up over all possible values of M and over all possible values of the rank, right? The rank can be at most t minus 2 over 2, let's say. And these things just get absorbed in the little o of t squared term. So we are done. So in fact, we have t squared plus little o of t squared. Okay. So we could find a KT-free graph which does not have too many independent sets. Okay, all good. Thanks, Aditya. Yeah, any questions on this? Okay, so if not, then let's take a break. So now we have a 15-minute break and then we start at 16:30. Let me write that in the chat. Yeah. As I said in the beginning, there are two parts to the main result that we want to prove, right? The existence of a nice graph, which doesn't have too many independent sets of size t and is also KT free. And this is what we have shown. So this is done. And now we need to focus on the other part. So this thing. Okay. So once you have one construction like this of a KT-free graph, which doesn't have too many independent sets, then how do you really obtain a coloring, an L coloring for an arbitrary L using this one graph such that there are no monochromatic KTs? And it's a very, very nice idea due to Victorson from, I think, inspired by an earlier paper by Victorson from 2019, where they had something similar combined with an argument of Condon and Ferber. So let's see what the really nice and new argument is. So here's how we will define our coloring. Okay, so say we have this graph. So say we have the construction and let G be such a graph on these many vertices with these many. It's due to okay, cool. Thanks, Yuval. Yeah, maybe you can link to the paper also, the original 2019 paper. I need Q. Oh, sorry, Sam. That's probably related to something else. Okay, yeah. Okay. So yeah, let's say we have such a graph that we just constructed with a equal to 5 over 8. And now we are going to construct a coloring of the complete graph on n vertices. And for now, let n be any integer. Later on in this coloring, we will choose a specific value of n, a specific large value of n. But for now, let's try to define a coloring for any complete graph on n vertices. Let m be L minus 2, and this is at least 0. And here is how we define the coloring. So the idea is to pick random maps. So pick these functions, m functions, from the set of n integers, 1 to n, to the set of vertices of your graph, uniformly and independently at random. So we pick m random functions, which will be something like a homomorphism in the end. But for now, we just pick some random maps from this vertex set to the vertex set of the graph. And we will use these random functions to define the colors, the first m colors of Kn. So now we are going to color the edges of Kn. And for the first m colors, we are going to use these random maps somehow. And for the last two colors, because remember the number of colors is m plus 2, for the last two colors, we'll just randomly color the edges in those two colors with like probability half. So here is our coloring. So yeah, give me a second. Yeah, so let x comma y be an edge of Kn. So any pair of numbers from 1 to n. Now, if there exists an I such that this thing f of I of x and f of I of y is an edge of the graph G. If there is some I for which one of these functions maps this edge of Kn to an edge of the graph G, then we color the edge. So the color of x comma y is equal to smallest such I. Okay, so we just go from f1 to fm. We just go sequentially. The first time we see some function, one of these functions, which maps this x comma y to an edge, we color that edge of Kn using that index I. So this defines a proper, this defines a coloring of some of the edges, right? So for all those edges for which there exists such an I. And if not, then the color, so if not, then this color is chosen to be either m plus 1 or m plus 2, and this is done uniformly at random. So with probability half, we color that edge using this color, and with probability half, we color the edge using m plus 2. So there are two random things going on here. First, we are picking these random functions. So these are the random blow-ups, we'll see. And then we are picking the last two colors randomly. And I guess this thing, yeah, the whole thing is from Condon-Ferber, and this idea is from the earlier paper of Hay and Wigderson. Yeah. Okay, so that's our coloring. This defines a coloring of the edges of Kn using L colors, right? Any question whether this definition, with the definition? Is the definition clear that we actually have a coloring of all the edges? I'll wait. Yeah, okay, just not. And now this is the claim. So if n is large enough, well, if n is this thing over here, which will fall out from the proof. So you don't have to, yeah, you don't just predict some n initially. You try to prove something and then n just falls out from that proof. So if n is large, then we claim that there is no monochromatic copy of KT. So there is no monochromatic KT with positive probability. And this would imply that there must exist some coloring for which we don't have any monochromatic KT, right? It's the same probabilistic argument that we saw earlier. Okay, and how do we show that? So we are going to show, so what we want to show is that the probability of there exists a monochromatic KT is less than 1. Right? If we can bound this thing as less than 1, then the probability that there is no monochromatic KT is positive. And for that, let's see. Okay, so let T, or let's say S. Yeah, let S be a T element, so a T subset of N. And we are going to first bound the probability that S is monochromatic. And then we are just going to use the union bound over all such subsets and show that's less than 1, right? The standard trick. So let's try to estimate what this probability is, right? So what's the probability that a given set is monochromatic? And here are a few observations. So observe that S can't be monochromatic in any color I which is among the first M colors, right? What's the reason for that? Maybe someone can say it in the chat. Why can't it be monochromatic in any of the first M colors? Yeah, we have a lot of time. This proof is the last bit of the lecture, so we can spend a lot of time with just one proof, on this one proof here. So why is this true? This was the coloring, if you don't remember. You can just unmute yourself as well if you want. By some nodding, I assume it's maybe clear, but you don't want to say it. So, okay. This is because Fi of S would then be a KT in G. If this was monochromatic, if all pairs of elements in S, they were colored using the same color I, where I is in the first M colors, then from the definition of our coloring, Fi of S, so for all pairs, and this by this I mean, yeah, you know what I mean. So all the pairs in S, they map to edges of G, right? So you get a clique there. Is that clear? Yeah. So S has to be monochromatic in the last two colors, right? So this, yeah, so this implies that S is monochromatic in M+1 or M+2. But this also implies that Fi of S is in fact an independent set. For all I. Because if some pair of elements in S was mapped by Fi to some edge, right? If that was an edge over there, then you have a problem, right? But because then we would have colored this using color I, and then it won't be monochromatic in the last two colors. Okay, so this is an independent set, and of course, of size less than equal to t. Cool. So now let's say, how do we go about this now? Be an independent set of size t. Yeah, so we want to now, so now we want to bound the probability. So now we want to find the probability that fi of s is an independent set. Okay, because then we will have the product of all those probabilities multiplied by the probability that it's monochromatic in m+1 or m+2. Because ultimately the probability that we are interested in is this probability. So product I equal to 1 to m multiplied by 2 to the 1 minus t choose 2, right? I can maybe write it differently so that it's not confusing. So it's 2 times half to the t, because this is the probability that it's monochromatic in m+1 multiplied by 2, because it's monochromatic in m+1 or m+2. So finally, this is the probability that we are looking for, right? Okay. So now we sort of start seeing that. So this is an independent set in G, right? So now because of this, we start seeing that maybe the number of independent sets of size at most t in G will play some role, right? That's why we are formulating it like this. Okay, so let T be an independent set in G of size less than equal to T. Now, what exactly is the probability that for some
This was
function?
mentioned in the chat. The exponent should be t choose 2.
Oh, sorry, of course, my bad. Yeah, so this is, yeah. Thanks, Yuval. So this is t choose 2, sorry. You color each pair and I don't do, yeah. Okay, and that's the answer. Okay, so what exactly is the probability that fi of s is a subset of t? Anyone? So fi was chosen uniformly at random, right? So you were just randomly mapping each point here to a point of the range, right? And s has t elements. So this is in fact the following, right? This is the number of vertices of the graph. And you have, so each element of S has the probability that's mapped to one of the elements of T. So this is the probability that gets mapped inside T. And then these are, it's a uniform map. So you do this, right? Okay. But then this is equal to, I guess, or this is less than equal to T divided by 2 to the T plus little o of T raised to the power T. So this is equal to T to the power of T, 2 to the power of minus T squared minus O T squared. And this thing you can just write as 2 to the T log T, right? So this whole thing is in fact just 2 to the minus t squared. Is that clear? Yeah. Okay, so we can just erase this stuff for now. Oops. And move this here. So this probability is less than equal to that. So this was for one independent set in G, right? One fixed independent set T. But now you can just go through all the independent sets of size at most T, and we have an estimate on the number of such things. So the probability that Fi of S is independent is at most the total number of independent sets, the total choices for T, the total number of choices for T, multiplied by that number. So you have 2 to the at squared plus little o of t squared multiplied by 2 to the minus t squared minus little o of t. So that's the probability that Fi of S is independent. And then you multiply, then you finally look at this probability here. So this thing is 2 to the am t squared minus mt squared plus some little o of t squared multiplied by 2 to the 1 minus t choose 2. So this is just 2 to the minus of, let me write it like this, t squared minus t squared by 2 plus little o of t squared. Okay, so that's the probability that one of the independent sets. So that's the probability, or that's an estimate of the probability that this S is monochromatic. And now you can just take the union bound. So what's the probability that there exists a monochromatic KT, and this is just the number of choices of S multiplied by this thing. So multiplied by this thing here, right? I can just so finally that's the probability we have. And this thing you can estimate again. Yeah, n choose t is just n to the t. So you have n times 2 to the, let's write it nicely, 2 to the 1 minus a m times t minus t over 2 plus little o of t raised to the power t. And now basically we are done, because if n is chosen to be something for which this thing becomes less than 1, let's say, then we are done. So if n is chosen to be 1 minus a m times t plus t over 2 minus little o of t, then the probability is in fact, yeah, it approaches 0. It's just little o of 1, right? As t goes to infinity. So in fact, with high probability, there will exist a monochromatic KT. And we are done. Okay, so any questions? Yeah, if you're not comfortable with these probability calculations, which I totally understand, especially for the finite geometry audience, then yeah, just please ask if any step is unclear. We have a lot of time. I'll wait. Let's get back to the lemma. So now we have done this also, and hence we have the result. And at this point, I should suggest again the following notes by Yuval, where he talks more about where these ideas are coming from and yeah, writing them down in a much more general form. I chose this 2 to the t plus little of t just for convenience, but yeah, you can of course write this as some number n and then make an estimate also. And you can in fact look at multicolor Ramsey numbers where for the first few numbers the clique size is fixed and then the last clique size goes to infinity and all of those cases, and you can really look at all of that in the notes. Right, so these ideas are very useful in this sort of a thing. Okay, maybe a silly question. Is there a way to use the local lemma to improve the union bound? Yeah, maybe Yuval can answer it. Probably it won't matter, I think. Yeah, I don't think asymptotically you'll get any improvement. But Yuval or Potu or anyone who was more
I think
comfortable
that's
with
right. It might improve the little o term in the exponent,
Yeah.
but I don't think it'll affect the main term.
Exactly. Yeah. So it might improve the little o term. Yeah. So we will still get something like this. Yeah. So I don't think it's really about using fancier probabilistic tools. It's really about finding better constructions with smaller a. That's where you'll get your improvements. So find new graphs which are clique-free and have a small number of independent sets. And let me leave you with a suggestion of such a graph. So here's something I just saw recently. Okay, so here is a graph which is very, very combinatorial. So you can look in the chat, and it has the same sort of properties in that it's clique-free, KT-free, and has roughly 2 to the t vertices. Now my question, which I will pose tomorrow as well, how many independent sets of size at most t does this graph have? Okay, that's the start to the open problem session for tomorrow. I have no idea. I asked, yeah, I have not really thought about this. So it will be fun to explore this graph. But also there might be some other nice graphs from finite geometry or whatever area. All you have to look at is this property, right? So you just want some KT-free graph with not too many independent sets. And any such construction will then immediately have a consequence for all these Ramsey numbers. Yeah, that's the idea. Cool. So then let me just say thank you. I'll end the lectures here, and then we can switch off the recording and chat a bit more if you want, or look at the inauguration of Joe Biden. Okay, that's